Okay, yeah, please roll whenever you're ready. Thanks.
Okay, so thanks for having me in the seminar. I am going to give 2 talks about the Hall-Strominger system and related topics. And today's one is about the existence problem. So for solutions of the Hall-Strominger system to exist, and some subtle obstructions we have found that we call Futaki invariance. This all is joint work with my advisor, Mario García Fernández, and will be part of my PhD thesis. So the main motivation, at least for me, for studying the Hall-Strominger system is what is called the rights fantasy, that put in simple words, has to do with the moduli space of Calabi-Yau threefolds. So in principle, this moduli space has different components, but they can be reached from one another through complex surgeries, which are called conifold transitions. And the proposal is that if we glue the different components along these conifold transitions, then the moduli space should be irreducible, should be only one component. So the Hall-Strominger system was proposed by Yau as a method of geometrizing, as having some control over conifold transitions, how to do them in a precise way. So yeah, this picture here is called the Calabi-Yau web, and in the axis you can see the non-trivial Hodge numbers of a Calabi-Yau threefold, the only ones which are undetermined. And in the horizontal and vertical axis, some combinations of them. So as you can see, the different Calabi-Yau manifolds are within a region which has on one diagonal, the diagonal on the right, has a Hodge number H21 vanishing, which means that it has no complex deformation. They are rigid. And on the other diagonal, it has vanishing Hodge number H11. So it cannot be Kähler. And so the projective Calabi-Yaus kind of interpolate between these two extreme behaviors. And conifold transitions, well, depending on the convention between conifold and reverse conifold, let's say they make points go to the left. So connect manifolds which are on the right part of the diagram, come across to the left. And it could very well be that if you do enough of these transformations, then you end up in the left diagonal, which is the non-Kähler manifolds. So even if you are interested only in the moduli of projective Calabi-Yau manifolds, if you are to follow Reid's proposal, then you end up in the non-Kähler realm, and this is why one should be interested in the non-Kähler geometry. So
I'm sorry, I have a question. So
yes.
What is a non-Kähler Calabi-Yau for you?
I'll give a definition just now. So it is a compact complex manifold whose canonical bundle is trivial, just that. But I don't assume there is a Kähler Calabi-Yau metric.
So are these simply connected?
They are either simply connected, or I think that their fundamental group can be finite. So finite quotients of simply connected ones. Is that okay?
Yeah, thank you.
Okay. So yeah, this is what I was going to say anyway. So for me, a Calabi-Yau manifold will be a compact complex manifold which has a holomorphic volume form, fixed. So a section of the canonical bundle which is nowhere vanishing. And well, for the purpose of this talk, you can think that this is a threefold, but most of our methods apply in any dimension. And I also want to give myself a pair of holomorphic vector bundles. Okay. Then what we understand as the Hall-Strominger system is a system of PDEs which asks for a Hermitian metric on a manifold and a pair of Hermitian metrics on both of the holomorphic vector bundles. So that we fix some real positive constant, alpha. The physicists think of it as some string tension. And the Strominger system is these three equations. So in particular, from the second one, you can already see that a solution to this system gives us what is called a balanced class. So a class in H22, which I consider in Bot-Chern cohomology, which is the class of a balanced metric. And in the literature, it is often taken as this V0 bundle to be the tangent bundle of the manifold, but we actually won't care about that. It can either be or not be. And we stress that for us, the Hall-Strominger system asks for both metrics on both of the bundles to be instantons, which is not always the case in the literature. Okay. So I will speak separately about what these equations tell us. So the first one, the instanton condition, is a condition about the stability of the bundles of the manifold. This is because of the celebrated Donaldson-Uhlenbeck-Yau theorem. This equation is equivalent for the bundles to be a slope polystable. The second condition is called the conformally balanced equation, or the Di Latino equation, and it's a condition about the complex topology of the manifold. As happens with Kähler metrics, it is not always the case that a complex manifold has a Kähler metric. And there are several topological criteria which one can check for a Kähler metric to exist, and it is the same with balanced metrics. And also, apart from the topology, it is a holonomic condition, because this equation implies that the holonomy of the bismuth connection is contained in the special unitary group. Or if you want to put it differently, the canonical bundle with the induced bismuth connection is flat. Okay. And so we are left with this third equation, which is the most difficult one, the most mysterious one. It's called the anomaly cancellation equation, or the Bianchi identity. And part of this talk,
I have a question. So when you say stability, you don't assume the metric is Bodichon or something? It is or Keller? So omega is just Hermitian thing.
Yes. So we are taking these equations jointly. So if you look at the second equation, you look that by a conformal change, by this factor of the norm of omega, you can see this is a balanced metric. So the stability goes in the same lines. Stability for a Kähler class or for a balanced class is very similar.
So you have a Kobayashi-Hitchin correspondence for those?
Yes, it even goes further for Godoshon metrics on just compact complex manifolds. But for the purposes here, I will take stability with respect to balanced classes.
Yeah, thank you.
Okay. So the question we want to address is the existence problem. So which are the balanced classes which are realized as solutions for the Hall-Strominger system? We fix the balanced class. We want to know if there are solutions within that class. And the strategy we follow is to kind of geometrize the anomaly cancellation equation. So find a gadget which has built in this equation and do geometry in there. So how we go about that? People who regularly follow this seminar already know a lot about generalized geometry, so I apologize if this is no material. I will speak about current algebroids and different versions of it. So I will have a manifold. Now I'm going to talk about jointly real or complex manifolds. So here K is my field, either R or C. When I say a manifold over K, I mean just real or complex. Okay. And then a current algebroid, which is the central object in generalized geometry, is given by the following data. First of all, we have a vector bundle over the manifold which fits in this exact sequence. Here, by this exact sequence, I only ask for exactness at the center. So there are no zeros at the start and end of the sequence. Okay. Then part of the structure is appearing on the sections which is symmetric and non-degenerate. Also, we have a bracket. For me, I will take the Dorfman bracket. Okay, so it's a bracket that satisfies the Jacobi identity, but it is not skew symmetric. The skew symmetry is in fact controlled by exact terms. But, yeah. And also we have a bundle map, which goes from the algebroid to the tangent bundle, and is bracket preserving between the Dorfman bracket and the Lie bracket. Okay, and also there are a bunch of compatibility actions between all these structures. Like the bracket is a derivation for the pairing. We have a Leibniz rule, etc. Also, yeah, what I wanted to say is that this definition is very general, and under minor changes, these objects exist either in the smooth real category, complex smooth, or holomorphic. And I will travel between each of them.
Sorry, Raul.
Okay.
Yeah. Can you just go back to the previous?
Yes.
Sorry, what is omega upper 0 lower x?
It's functions.
It's just smooth functions. Oh,
yes,
okay.
it's or zero forms if you like. Yeah, and
okay.
the K denotes real or complex functions. Okay.
Yeah.
Fine. So the most basic example of courant algebroids is the one that are called exact courant algebroids, and are the ones which fit in this exact sequence. So these are defined abstractly, but if you take an isotropic lift, so a lift of the tangent bundle to the whole space that is isotropic, that is that the pairing of any two sections is 0, then we have a nicer presentation of this algebroid in terms of a split tangent plus cotangent. Then we have very simple formulas in this model, which are given by these ones, and another one from the anchor. Here for the bracket, there is a 3 form that is determined by this splitting that is closed. And if I choose another isotropic lift, then I have another 3 form. So the 3 form is not well defined, if you like, but its cohomology class, which is usually called the Severa class, is. Okay. And then this was for smooth exact courant algebroids, but we also have a holomorphic version in which this 3 form is not just any 3 form, but has these 2 by degrees, has components in 3, 0 and 2, 1, and being closed implies in particular that the 2, 1 part is Dolbeault closed. And then with this requirement, we can hook up a twisted Dolbeault operator. I said twisted because in the splitting, tangent plus cotangent, it is smooth, but it is no longer a holomorphic sum. If it was a holomorphic sum, here in the expression of the Dolbeault operator, I would have only the first 2 terms, and then the twisting comes with this component H21. Okay. So yeah, this is how it goes. There is a very geometric way to implement the holomorphicity on this bundle, and I will talk about that in a moment in a more general context. Okay, we'll come back to this afterwards. So now okay, so here sorry, I cited incorrectly. So Gauss theory for string algebras for Mario García Fernández and other authors. I forgot to cite. Sorry very much. So I want to talk about string courant algebroids. First, I want to talk about the smooth version. Okay, so I will give myself some new ingredients. For this, I will write in red the new ingredients as opposed to the black ingredients I had before. So I'm going to compare this new string version with the exact version. So the first thing I want to have is a quadratic Lie algebra, either complex or real, and that is a Lie algebra with a pairing that is adjoint invariant. And I will assume no positivity on the pairing, okay? Just non-degeneracy is enough. Then associated to this Lie algebra, I have a connected and simply connected Lie. Okay. And then the next thing is a principal bundle that is a principal bundle for this gauge group, and with the condition that the first point tracking class is vanishing. The reason why this is so will become apparent in a moment. So from this principal bundle, I can hook up what is called the Atiyah algebra, which is the reduction of the tangent bundle of the total space by the action of the group. And then the new exact sequence in which this bundle fits is this one, in which the tangent bundle is replaced with the Atiyah algebra. Then, as we did in the exact case, we can have a simpler presentation just by taking some elements in the geometry. So before I had an isotropic lift, now I have furthermore a principal connection, and so the presentation of the string algebra is given by the same terms as before, and there is also one new actor appearing. This is the adjoint bundle of this principal bundle. Okay. And then we can enlarge the formulas we had before for the pairing, for the bracket, and for the anchor. And so these formulas can be already derived from the just exact current algebroids if you see them as exact current algebroids over the total space of the principal bundle and perform reduction for the action on the group and consider just invariant sections, then you end up with these formulas. So they are kind of natural. Okay. And so as before, we had an equation that encoded the axioms of the algebroid. So before we had a closed tree form. Now we no longer have it closed, but we have a correction term. And this explains why we are obliged to have a first point tracking class vanishing, right? Because this term here is exact. So okay, so far so good. Now I will consider a special kind of string algebroids, which are the complexification of real ones. Okay, so I have my complex manifold. I have a real string algebroids in the terms before, and then I consider its complexification. One warning I have to make is that not all complex string algebroids admit a real structure, so they are not always of this kind. Okay, they are not always the complexification of a real one. Nevertheless, I can consider this, and I have a definition for what I said before, that I was going to explain how to implement the holomorphicity. I should mention that these structures that I am going to introduce have been already thought about in the exact case in the paper by Mario García Fernández, Jeffrey Streets, and Joshua Jordan. Now I'm going to discuss them in the string context. So, okay, the first structure I want to introduce is this bundle, which I call a lifting of the anti-holomorphic tangent bundle. And I call that a lifting if it satisfies these conditions. So it is isotropic, involutive with respect to the Dorfman bracket, and that such that the anchor projects isomorphically to the tangent 0,1. Okay, this will be my notion of a lift. And the thing is that with this lifting, one can produce a holomorphic current algebroid. How come? So if you take this construction, so L perp with respect to the ambient pairing, mod L, this inherits all the structure of a current algebroid from the pre-existing before. So from EC, you get a new pairing, a new bracket, and a new anchor. And the thing is that it is moreover holomorphic by this formula I give you here. So just taking profit of my of the subbundle I have defined, since this was an isomorphism, I can take the inverse image to pull up tangent 0,1 vectors to the total space, and then use the ambient bracket to define a Dolbeau operator. Moreover, this Dolbeau operator is going to be integrable just because of the axioms. The Jacobi identity makes this operator integrable. So we indeed have a holomorphic current algebra, okay, of a string type. The next ingredient I want to have is some Hermitian geometry, and the geometric content is given by a generalized metric. So in this context, a generalized metric will be a subbundle such that the following things happen. So when I restrict my pairing to the generalized metric bundle, then it will be positive. Okay? And it has the same dimension as the tangent. So it is a graph of the tangent, if you will. And as it happens in exact current algebras, whenever I have a generalized metric, then I can split my string algebroid in two halves. But here they will not be halves. I have a generalized metric and I have a complement, which is the perpendicular part. But the new warning is that, as opposed to the exact case here, the pairing restricted to the complement, to the V minus, is not negative. It is not assumed to be negative definite, and in fact, it will be false for all our interesting examples. Okay, so the pairing restricted to V plus is positive, but the other one will not have a definite signature in general. Okay. And one more thing is that whenever we have a generalized metric, we have some data determined. So here we have a Riemannian metric, and we have a splitting in the terms I said before, and there are determined a free form and a connection on the principal bundle, or this construction is on. And in terms of this data of the metric in particular, we have a nice presentation of the generalized metric and its complement, okay, given by this expression. So this is a graph of the tangent, and this is a graph of the tangent plus the adjoint of the bundle. Nice. So then the good definition, the compatibility between these two structures is the following. So I say a generalized metric is compatible with the complex structure of the manifold if it happens the following. I take the generalized metric, I complexify it, and I see those elements that project to the tangent 0, 1. If that bundle is a lifting, then I say that my generalized metric is compatible with the complex structure. Okay. This definition is so that the following happens. So if I have a real string algebroid and a generalized metric, I consider its complexification, and I consider this data that was determined by the generalized metric. Then the Riemannian metric gives rise to a Hermitian form. Then, according to the definition before, the pair, the generalized metric and the complex structure are compatible if and only if this is indeed a Hermitian metric. So it has by degree 1, 1, and we have this formulae. So the 3 form is the torsion of this metric. We call in Hermitian geometry this term usually the torsion of the metric, and the 0, 2 component of the curvature of the connection is 0. So we endow the bundle with a holomorphic structure given by the 0, 1 part of this connection.
Sorry, Raul, just so I understand, I mean, yes, like script J here is just a classical complex structure.
Yes.
And it also determines what you mean by sort of the complex structure on the...
Is the complex structure on the manifold. We say, yes, so it's the complex structure of the manifold. Yeah, that's it.
And it sort of also determines what you mean by the holomorphic structure on Q as well, or?
The holomorphic structure on Q is determined by the lifting you take. And here the lifting will be, in fact, induced by the generalized metric. So on the one hand, I have a notion of a complex structure and a complex manifold, and I ask for a compatibility between the generalized metric and the complex structure on the manifold.
I see.
And on this, yes.
So like
And
that's
on the
really
other-
what's meant in the first definition, in the definition on the slide. It means compatible with the complex structure on the base. That's what it means.
Yes, yes.
Yeah, okay, I understand. Thank
Absolutely.
you.
Okay, so I think we can continue. And if we plug this in, this form of the three form of the Severa form, in the equation encoding the axioms of the string algebroid, then we arrive at this expression, which is very similar to the anomaly cancellation equation. If you have that equation in mind, we just have to do a little modification to end up with the anomaly cancellation equation. So okay, we then come to this result. So I have introduced some structures on a string algebroid, and because of these structures, we will have different presentations of a string algebroid, which go as follows. So if I have a real string algebroid and a generalized metric that is compatible with the complex structure in the sense before, then my holomorphic string algebroid was constructed as a reduction, is isomorphic to the complexification of the complement of the generalized metric, just by the map induced by the projection to the V minus. Okay, and as we saw before, this was the graph of the tangent plus the adjoint, and upon complexification, this is an isomorphism between the complexified tangent and the complexified of the adjoint bundles, which is the adjoint bundle of a complex principal bundle. Okay, so here PC stands for the complexified principal bundle of P. And I will take profit of these different incarnations of how to see a holomorphic string algebra. Okay. Now, if this is the first place I will use it, then we can construct a generalized pseudo-Hermitian metric on this holomorphic string algebroid in the following way. So in the isomorphism I described before, we can see the different sections. There is a typo here. Different sections as sections of V minus. So we can just take the sections as being in V minus, pair them with the ambient pairing, and just flip a sign. And this is a Hermitian metric, but because I said that the pairing restricted to V minus was not assumed to be positive, then this Hermitian metric is no longer a positive Hermitian metric. Okay, so in the exact case, it can be done the same, and in that case, it is a Hermitian metric, but here it is no longer. Okay, coming from the fact that the quadratic Lie algebra I started with has a pairing which I not assumed to be positive. Fine, this is all the structure I will need. So I will now make a recap of what we know so far. So I have a complex manifold, and I have a complex principal G bundle for a complex Lie group, and I assume that the Lie algebra has a pairing adjoint bundle, so a quadratic Lie algebra. Then I assume given a solution of these equations, which seem very similar to the anomaly cancellation equation. Then what I said is that we can produce a holomorphic courant algebroid of string type, and we can make it isomorphic to this bundle, to the complexified tangent plus the adjoint of the principal bundle. And we can furthermore endow it with a Hermitian metric. We don't know nothing about the signature. This will play a very interesting role. Okay, so now the thing I want to do is to link this with the Hallström system, which was sort of my aim from the start. So what I do for that? So I can, this construction was for a general principal bundle. Now I choose that principal bundle to be the bundle of split frames of the holomorphic vector bundles that were involved in the Hallström system. So I choose the bundle of split frames, and then Q has this nice presentation. the complexified band, the complexified tangent, plus a factor for the endomorphisms of each of these bundles. And then the pairing I have on the Lie algebra is, so take one of these factors, one factor endomorphisms of a vector bundle. The pairing will be to compose two endomorphisms and take the trace. And I will take the trace with different signs in each of the factors. And if I replace that in this anomaly cancellation equation above, I will get exactly the one for the Hallström-Inger system. Okay, and now that I have chosen holomorphic vector bundles, then I can replace the unknowns of the connections just by Hermitian metrics and say that the connections I was looking for are the Chern connections of this metric. So what I have done in few words is encoding a solution to the anomaly cancellation equation of the Hallström-Inger system in terms of a string algebroid, together with a Hermitian metric of possibly indefinite signature. Okay. Yes, this is this is the main message of this part of the talk. So I have a solution to the anomaly cancellation equation written again here. This is in the exactly same terms as in the Hallström-Inger system. Then I have an associated holomorphic current algebroid. From now on, when I say holomorphic current algebroid, will mean the same thing as string algebroid, and will mean the same thing as having a real structure. And I will make no difference between these things. For me, it will always be this way. Okay, so then one last abstract thing I want to introduce is the Chern connection of this data. So this is a holomorphic vector bundle. I have a Hermitian metric. Then I can consider its Chern connection. So it is given by this expression, which you can see is fairly natural in generalized geometry. I only use the ingredients that generalized geometry gives me. So I have a generalized metric I use to lift elements from the tangent, and I have projection to the B minus, the complement of the generalized metric. So how does the connection act? So you lift a vector to the generalized metric, you take the ambient bracket, and then you take back this resulting element to Q via this isomorphism I write here, B minus. So now what I want to do is to say what a whole solution to the Hallström-Inger system means in terms of this generalized geometric data.
Wait,
so
sorry.
Yes.
Sorry, Raul. I guess like in the exact case, I mean, this Chern connection, it just is the usual Chern connection of a Hermitian metric on a holomorphic vector bundle. Is that no longer the case here, or? I mean, like,
so
this
is
just a complicated way of saying that, or?
It's a Chern connection on a current algebroid. In the case it is exact, so it is the Chern connection of an exact current algebroid, which is holomorphic, and the holomorphic structure is produced with a pluriclosed metric. Pluriclosed metric because in the anomaly cancellation equation, you no longer have these bundles. Does that make sense?
Well, I guess my question is just, well, sort of like underneath the structure of a holomorphic current algebroid is just a holomorphic vector bundle. And in the exact
of course,
case,
this is a Chern connection in that. Yes. It's
okay, yeah, that's all.
Yes.
I just want to make sure. I mean, you're just
Sure.
sort of able to write it explicitly using the sort of objects
That's the nice thing.
intrinsic
Yeah,
to generalized geometry. That's the point.
Yeah, that's the point. Yes, I have this is a Chern connection in classical complex geometry, and now because this is a holomorphic current algebroid, so there is extra structure, I am able to write it in generalized geometric terms. If you like.
Okay, yeah. Thank you.
So as I said, this construction up to now asked for a solution to the anomaly cancellation equation just by itself. But I recall that the Hallström-Inger system has more equations. There are more conditions. So I want to see in this current algebroid.
If I can make a comment, yes, that this is there is an analog expression in my paper with Jeff and Josh, which we call the bismuth identity. This is essentially this thing in the exact case is what we call the bismuth identity.
Okay.
If it clarifies.
That makes sense. Yeah, thank you.
Yeah, I will say a word about that. So yes, I was saying that a whole solution to the Hallström system, I want to see what does it mean in terms of the generalized geometry I have introduced. Okay, so this is my next goal. So to do computations, I choose this my favorite identification. So I choose the corresponding structure so that I have an identification between the holomorphic Grant algebroid and this bundle here. The tangent, the endomorphism, the unitary with respect to this metric, the unitary endomorphisms of both bundles. And this is all complexified. And that's what I was saying, that the Hermitian metric is no longer positive is because of this middle term. So this term alpha trace V0 is what is going to make this metric indefinite, but I just need it because this is how the anomaly cancellation equation of the Hallström system is recovered. So I really need to take this Hermitian metric. This is going to be an indefinite unless I have no V0 bundle. Okay, so unless there is no term. So I cannot escape from this fact. This is something that is built in the field from the very start. And then,
by the way,
yes.
I have a question. So starting with a solution of the Hallström system, starting with a solution of the anomaly cancellation equation, you have produced a holomorphic string algebroid with this Hermitian metric of indefinite signature on the bundle, right? So can you go backwards? Like if you are given a holomorphic, no, backwards isn't. I mean, can you? Is the converse true? Like given a holomorphic string algebroid and a Hermitian metric G, capital G on it, can you retrieve a solution of the anomaly cancellation equation?
Yeah, okay. It cannot be any Hermitian metric. It has to be of a very special form. So I have written here what is the expression for how this for how the chain connection looks, for example. So it is not any metric that you have in the. Okay. But if you choose in terms of the generalized geometry, if you choose a generalized metric that is compatible with a complex structure in the sense I said before, then you do get a solution to the anomaly cancellation equation.
Okay.
Okay.
Thanks.
So yes. So I had an abstract result about how the chain connection is. Now I want to see it in precise terms. I want to do computations. So in this identification, this chain connection looks like this. This is related to Mario's comment. So here in the upper left part, you see one connection that I call nabla minus appearing, which is this connection. Is nabla of Levi-Civita plus one torsion term. And this torsion term is the opposite of the torsion terms that appear in the bismuth connection. So it is like kind of the same connection as the bismuth connection if you flip the sign of the torsion. Okay, this is this weird connection with torsion appearing. It is not unitary even. It is this orthogonal. And when I just drop the bundles, if I just consider both of them to be nowhere, then I am left with this upper corner. So the chain connection is just this connection, which is sometimes called the Hall connection. This recovers an old observation by Bismuth. This was what was said before. So if I use a metric to identify an exact current algebroid with a complexified tangent, then using a pluriclose metric to construct a twisted Dolbeau operator, then the chain connection of this data is sent to this nabla Hall. Okay, this is a stringy version or a string algebras of this observation. Of course, Bismuth didn't speak about generalized geometry or any of this stuff, but the content of is just the same. Okay, So then I can go on. I have a chain connection. I can ask for the relevant curvature properties of this connection. So I have written here just to get a glimpse of how the curvature is, the full curvature tensor of this metric. And I have here a wealth of Hermitian geometry terms appearing. So you don't need to remember any of this. I just show you because I was interested in this. So here is appearing many things. You see here the torsion of the metric, see the curvatures on the bundles, you see this Hall connection coupled to the connection on the to the chain connection of the bundles. There are many things going on. This is all written in terms of classical tensors. So we have traveled from the generalized geometry to standard differential geometry to do the computations. Any questions up to now? Okay, so I carry. Then we come to the main result of this talk. We got this very nice result. So suppose you have a solution to the full Hall-Strominger system, not just of the Bianchi identity. Then a solution to this Hall-Strominger system, we already know that it produces a current algebroid, which is holomorphic, and that it has a preferred Hermitian metric. Then if this is a solution to the whole system, then it satisfies this Hermite-Einstein condition for the curvature on the string algebroid. So here I have to make a few comments about this. So this equation, which seems familiar, this is Hermite-Einstein equation, is not quite so, because several things. On the first thing is that this metric is not positive. Okay, so it is not a Hermite-Einstein condition in the classical sense. Also, this is a very coupled equation because the Hermitian metric omega is appearing in the representative of the balanced class, and also is appearing in the inside of the Hermitian metric of the current algebroid. Okay, so this is a very coupled equation. And several remarks I have to make about this is that this is inspired by some result that appeared already in the physical literature, for which this is an exact counterpart of what appeared as a perturbation result. In this paper, in the year 17, De La Osa, Lasfos, and Svans showed that with a reduction from what they call a heterotic G2 system, which is kind of the same thing as the Hall-Strominger system, but in 7 dimensions, in 1 dimension more. And performing reduction, they were able to see that a solution to the Hall-Strominger system is equivalent to having this this kind of Hermite-Einstein condition to all orders in perturbation theory. Here in our context, this result is only one directional. So if I have a solution to the system, then I hook up this Hermite-Einstein metric. But in strictly weaker assumptions, this also holds. I will speak more about this next week, but for the moment, just let you know that this is not an equivalence. So we have some context in which we have string current algebroids with a Hermite-Einstein metric, but which do not satisfy the Hall-Strominger system. And one last thing, yes.
Sorry, Rogue. I don't think I quite understand. Well, what's the extra condition? Or so you say you have string algebroids that satisfy this sort of Hermitian Einstein type equation, but somehow it does not correspond to Hall-Strominger? That's what you're saying?
Yes, I say that a solution implies a Hermite-Einstein equation, but the converse need not be true.
I see.
So
what is
there is
yeah.
Let me put it this way. So I have from the start worked in a non-Keller-Calabi-Yau manifold, for example. So particular, the canonical bundle was trivial. And I say that I am able to prove this also for manifolds whose canonical bundle need not be trivial.
I see.
That
But
cannot
with that
solve the
homological
Hall-Strominger
function-
system, never ever, okay?
I see, I understand.
But under weaker assumptions, you can also make sense of this. Okay, there is a weaker theory which implies Hermite-Einstein metrics on current algebras.
Okay, yeah. Thank you.
I will speak more about this next week. Okay, but this was not part of today's talk. And as I said before, these operators that I showed you, these metrics, were in terms of standard differential geometry, standard tensors. So we have proved this by means of hard Hermitian geometry, hard manipulations. But we are kind of looking for a more high-minded generalized geometric proof, which for the moment, we don't have. Okay. So now we are going to exploit this result. And what are we going to do? We are going to hook up some invariants whose vanishing or not determines determines an obstruction for the Hall-Strominger system. Let's see how this goes. So the Hermite-Einstein equation has a moment map interpretation. And whenever this happens, whenever you have any equation that has a moment map interpretation, you have an associated invariant, which we call Futaki invariant, by comparison with the classical Futaki invariant, which was developed in the context of, in a different context, in studying scalar Kähler, scalar, how do you say this? Scalar curvature Kähler metrics. But we just generalize this notion. Whenever you have an equation with a moment map interpretation, you have a Futaki invariant associated with it. Okay, so for this, I will ask you to put aside what I said about generalized geometry up to now, and just get your basic complex geometry to understand this result. This result is very classical. So if you have a compact complex manifold and you have a balanced class, considering Botcher homology, okay, and you have moreover a holomorphic vector bundle, then I can consider this map. If you give me a holomorphic endomorphism of the bundle, I can produce this character. So I precompose with the curvature of some chair connection of a metric, take the trace and evaluate it against a representative of this balance class. So if I chose H and omega such that it satisfied the Hermite-Einstein equation, so if this equation at the bottom was satisfied, then this Futaki invariant would obviously be vanishing. And what I say is that this quantity does not depend on the representative of the balance class and on the metric I have chosen. It does not even depend on the signature of the pseudo-Hermitian metric I choose. Okay. So this is a character that tells me when a bundle has a Hermite-Einstein metric or not. And for the Hermite-Einstein metric, I do not even care what its signature is. So this is what we are going to use, but now in the context of the current algebra I was discussing before. Okay, so the difference between this classical proposition and our setting is that our Futaki invariants do not come by themselves, but they come in families. And how is this so? So for this, we appeal to this proposition by García Fernández Sabazi, Rubio, and Tipler that proved the following thing. So if I have a non-Kähler Calabi-Yau manifold and a pair of holomorphic vector bundles, this is the geometry I started with, then they are able to classify all of the holomorphic current algebroids that extended the holomorphic vector bundles. And the classifying space is just an affine space. This affine space is understood in cohomological terms. So if you have the del operator on forms now induces a del operator between apli cohomology and cohomology of some sheaf complex. Okay, so then they say that the image of this map gives the classifying space of holomorphic current algebroids over the holomorphic vector bundles. So what we say now is that for each of these holomorphic current algebroids, I have a Futaki invariant. For each point in the classifying space, I have a holomorphic vector bundle. And then for this one, I have a Futaki invariant. And then I can consider all these in families.
Sorry, I'm really confused. So these Futaki invariants, we think of them as some sort of object coming from moment map picture. I
Yes.
kind of completely confused what's going on. Can you try to explain what's your GID setting exactly?
Yeah, okay. This was like just a comment. This was coming from a moment map interpretation, but here for simplicity, we don't really need any of this. We just can consider this result. Would you be happy with that?
So what is this little phi in the notation?
Yes, we have a holomorphic vector bundle, and then we take a holomorphic endomorphism.
Okay. Okay.
And then
so
we take this formula. In case there is a Hermite-Einstein metric, then this vanishes.
Okay. So so this endomorphism, you consider it as a gauge, as kind of a
Yes. Yes, in the
gauge group. And then okay.
yeah, this
Okay.
has a gauge interpretation.
Yeah, that makes sense.
So yeah, just in case it clarifies, so this is just associated to the moment map for the gauge. So for the unitary gauge group acting on connections, but there in the space of connections you put some presymplectic structure,
Yeah.
which may not be positive definite with respect to the complex structure on the money.
Okay. Okay. Thanks.
Thanks. So what I was saying is that our Futaki characters come in families because the families of holomorphic current algebroids have a classifying space given by the image of this map. So for each point, I have a different current algebroid, I have a different character. So now, this I wrote it as a theorem, but it is just a consequence of what I said before. If I have my geometry, a Calabi-Yau manifold and a pair of holomorphic vector bundles, I can consider the classifying space of holomorphic current algebroids given by the criterion before. So if I have a solution to the Hultstrom-Linder system, then I already know that I have a Hermite-Einstein metric of possibly indefinite signature on some holomorphic current algebroid. This tells me that there is some point in the classifying space of these objects for which the Futaki invariant vanishes. So there is some point in the classifying space for which this holds. This Futaki invariant against the balanced class of the solution vanishes. Okay. And this is what we are going to use as an obstruction. So thinking in the converse way, we have the following. So let me put these two things together. We say that if we have a solution to the Hultstrom-Linder system, this solution is within a holomorphic current algebroid just if the associated holomorphic current algebroid is in the same isomorphism class in the construction ISP. So the conclusion is that if we are able to compute all the Futaki characters for all possible elements in the classifying space of homomorphic current algebroids, if we know that all of these characters are non-vanishing, there is no single holomorphic current algebroids that supports a solution to the Hultstrom-Linder system, okay, for a fixed balance class. And this is what we are looking for. We are looking for all the members of a family indexed by this classifying space of holomorphic current algebroids to have non-vanishing Futaki characters.
Yes, Raul, in the definition
Yes.
you gave, in the definition, the Chern connection plays no role, right? It's just Q being isomorphic to QS.
Right. Right. Yeah, this is a bundle thing. Yeah, thank you. Yeah, so I repeat here what I was saying. If I am able to find if I am able to prove that all the Futaki characters in the family indexed by the classifying space of holomorphic current algebroids are non-vanishing, then I can say that within that balanced class there is no solution for the Hallström system. I am always saying the same thing in different ways, but it's the same result. Okay. So this is what we are looking for. So a fact that simplifies our life is that in manifolds, which are, let's say, near algebraic manifolds, so manifolds satisfying the Del-Del-Baran lemma, the classifying space for holomorphic current algebroids reduces to a point. And in that case, our family of Futaki characters reduces to a single Futaki invariant. That is what we call a Futaki. Okay. And this is what I was discussing at the very start. In the motivation, I said that the rate fantasy was supposed to be geometrized by the Hallström system. If I am able to show that for certain bundles there is no solution for the Hallström system, then maybe we have to rethink or to refine how this geometrization procedure or how the conifold transitions have to be performed. And so this Calabi-Yau web, which was connected along conifolds, then may appear no longer as a web, but rather as a labyrinth in which there are walls that we may know that exist because of these obstructions we have found. Okay, this is the main message. So now here, just to give you a glimpse in practical terms of how our Futaki invariants are, we compute them in terms of classical tensors. So for a holomorphic current algebroid, we take an endomorphism and we write it in terms of several things. Here, I don't think I will give all the details. Just to give you an impression of what this amounts to in the end. So here there are a lot of things appearing. So there are metrics appearing from the balance class. Metrics appear because of the solution we are looking for. There is the bismuth connection. There are a lot of things. Also the ones coming from the holomorphic endomorphisms. Okay, so it's actually can be a quite difficult thing to compute. So now, how am I doing with time? Okay, it's 1 hour now. Okay, so I'm nearly finishing. I just wanted to discuss a practical example of these computations and to reach the results we have so far applying this theory. So for this, we applied to the case in which the computation is most simple. And how do we do this? So we consider a family of complex nil manifolds. The nilpotent Lie algebras, which support a complex structure and balanced metrics, are classified. There is a full classification of them. And we take some of them, which are in this classification called H2, H4, and H5. And then for each of these, we have a frame coming from in the tangent bundle. We have invariant vectors at the Lie group level, and by quotienting by a lattice, we get a frame in the nil manifold. Okay? And then we do the same thing for the tensorial associated bundles of the tangent bundle, for the cotangent, for the exterior powers, etc. And so the information of the Lie algebra and of a complex structure that is invariant, that one can put on this manifold, is equivalent to some structure equations I have here. And then many of the geometric computations one can do, you can do them on a linear algebra level, let's say. So this example is a modification from one we found in a paper by Fernandez, Ivanov, Ugarte, and Villacampa. And this nil manifolds is, as I said, a Lie group that is quotiented by a co-compact lattice, and we produce a manifold in which we have a complex structure, and that it has a fibration over a torus, for just a complex two torus. So then, this is the geometry of the manifold, and we are able to give it an SU3 structure just in the terms of this frame I have above. So omega 0 here is a balance metric given by this expression. This manifold is Calabi-Yau, non-Keller, in the sense that we have a holomorphic nowhere vanishing volume form. And we have a balance class. It is the balance class given by this expression of this data. And then to have solutions or not to the Hall-Strominger system, in the first place, I need vector bundles. So in the most simple case, I can choose line bundles. I will have just one of them, the V0, okay? And I take the V1 to be the trivial rank 0 vector, no one. For the V0, I take a line bundle which is basic. Okay, so I take a line bundle over the torus and I pull it. And then I identify these bundles by their curvatures. Okay, so I have a family of curvatures indexed by integers. So all of these forms determine line bundles with different topology, but which have a Hermitian metric that has this curvature. So for them, I am able to solve the Bianchi identity for some value of the tension of the string, this parameter alpha. So if I have a solution just of the anomaly cancellation equation, then I have an associated holomorphic current algebroid, and I can test the Futaki invariants in this algebra. So then the result is the next one. So I have the geometry that I explained before. I have this manifold, which is Calabi-Yau, and then the space of the classifying space of holomorphic current algebroids that extend this line bundle has a complex dimension 4. Okay, so it's real dimension 4. This is a real. And we are able to prove the following. So for any point in the classifying space, apart from the point 0, corresponding to this Q0, apart from that point, the Futaki invariant does not vanish. Okay, so in view of the results before, this means that these current algebroids, apart from the central one, do not support a solution to the Hall-Strominger system within this fixed balance class. Okay, so we are in this case we are like successfully able to know when a solution does not exist, because for all points we either for all points, I mean for all points classifying holomorphic current algebroids, we either find a solution of the Strominger system or we obstruct it. So in this sense, this obstruction is the best it can be. Okay, so next, what we would like to do is to find a counterexample in the most strong way. So the strongest way we can think of is to consider some holomorphic vector bundles and to obstruct each of the holomorphic current algebroids over them. So if all this family is obstructed, then we know that there is no solution whatsoever for these vector bundles. We have yet to do this. We are progressing, but we are not yet done. But we have confidence that this will be possible. Okay. Also, the whole point of this was to test the plausibility of Wright's proposal about race fantasy. So we should do this on algebraic freefalls. We don't know if this if we will be able to do this, but we will try to choosing classes, balanced classes, which are on the boundary of the balance cone, because we have some suspicions that within the realm of algebraic threefolds for balanced classes, which are squares of Keller classes, there is some solution to the Hallström system. But if we reach the boundary, then this may not be possible. And there are some works in this direction. And yeah, one last aspect is that we have Hermitian-Einstein metrics on current algebras, but which are not positive. So in principle, this does not produce any stability, any sensible stability condition, because the classical Donaldson-Uhlenbeck-Yau theorem works for positive Hermitian metrics. So one thing to think about is whether we have some counterpart in the case of this indefinite signature. Okay, and if we are able to produce GIT obstructions, or in the best of cases, a Hitchin-Kobayashi correspondence in terms of solutions to some differential equations, like the indefinite signature Hermitian-Einstein equation, and stability conditions for string algebras. Okay, so I will speak more of this next week. And this is all I wanted to talk about today.
Yeah, thanks, Raul. Thanks. Are there more questions?
Yeah, I have a kind of a probably silly question, I don't know. But this Futaki invariant is just one appearance of some boundedness of energy, of Mabuchi energy. So Futaki must vanish if the Mabuchi energy is bounded. Do you have such a functional in this indefinite Hermite-Einstein setting that you expect to be bounded for a solution to exist?
So for the moment, we have not worked in that direction. I take the recommendation. We will look at that, but I have nothing to say that in that respect. I don't know if Mario wants to.
Yeah, maybe the material of the next talk maybe partially answers your question. So I guess the answer is possibly. I mean, one thing we certainly know is not the analog of Donaldson functional because of this issue of the metric being pseudo-Hermitian, and there is a way of fitting this into a 34 harmonic metric. So possibly, an answer to this is some sort of flow. I mean, of the type that appears on for Hitchin equations. So coupled with a Higgs field, that could possibly be the answer, but we don't know because the equations are very coupled, so it's unclear whether the contributions from the different terms are going to make this functional convex or not.
I see.
I was curious too. Do you have a sense, like what so if you fix a balance class, like the space of which string parameters S, but like I guess in this example you discussed in the nilpotent, like with this nilpotent Lie group, there was a unique parameter, right, which admitted a solution, all the others didn't. Is that right? I mean, is that somehow a general feature, maybe, or like I don't know. I mean, I guess maybe I wonder how this Futaki character like looks as a function of S somehow. As a function.
So there were like questions. The first one is that we do not expect that this is a general feature. So what we are looking for is for some bundles in which this is obstructed all the way for all the S's. Okay? It should be easier if we are able to look in manifolds for which this parameter reduces to just a point. So for manifolds satisfying the Delta-Bar lemma, particular algebraic manifolds, and there are also, so this is not even necessary. There are some manifolds that would happen to satisfy this, and yeah, so.
But I guess I'm asking, like, if you have a solution for one string class, is there a reason to think that maybe that's the unique string class for which there's a solution or something? Or are there spaces for which every string class has this? I mean, I have no idea really.
Yeah, for the moment
Understand
we
that
have
it-
observed a variety of behaviors. So we have observed this one in which there is a single parameter for which the Futaki does vanish. We have some of them which have solutions in different string algebras, and we have some examples in which we don't know if there is a solution, but the Futaki invariant vanishes, so we cannot see anything.
I see.
So yeah, there is a
Yeah,
variety.
right. Okay, yeah, I understand.
Yeah, but there are bundles for which several string classes have solutions.
And
Yes,
I mean,
clear.
is it like a convex set? Is it like a linear subspace of the space of string parameters or something? Or
Okay, so in our examples, this is a linear subspace, but if you want like your metric to be a metric, then you are, yes, restricted to an open set in which the non-degeneracy, the positivity holds.
I see. I see. That's interesting.
What does the vanishing of the string class mean for the string algebroid? Does it mean that it splits as holomorphic vector bundles?
No, nothing of the sort. It's just that we found an easy solution to write down, and we choose that as the origin of the affine space. Okay, but
I mean, it really is an affine space. It's not a vector space, the class affine
yes,
space.
yes.
Oh, yeah, right. Okay, yeah. No, I remember. Yeah, right. Yes. Okay.
Yeah.
Okay.
All right. Well, I don't know. Any others? Well, if not, let's thank Raoul again. It's very nice.